Right, this is the start of Unit 2. We're going to be learning more about radicals. Today's lesson is 2.1. We're going to be learning how to simplify radicals. Go ahead and put today's date up here if you'd like. What is a square root? We should already know what this is, but a square root is having a radical, which here's the radical sign, that has an index of 2. But we know that they will never have that 2 written if it's a square root. Right? That's the only time. But if it's a cube root or a fourth root or a fifth root, it will always have a number here. Another word you might have never heard of is the radicand. The radicand is the number or the variable under or inside the radical. But all of this together makes up a radical. Now let's talk about what are perfect square numbers. So I want you to imagine that I cut out a bunch of little squares and I handed them to you. And I gave you different numbers and I said, okay, I want you to count out that many squares and see if you could put them together or arrange them into a bigger square. Well, first of all, you would have to know that a square has all 4 sides are the same. So what we're saying here with perfect square numbers is they can be arranged into a literal square. In other words, it's the product of a number contains duplicate factors. The first smallest perfect square that I don't have on here is actually 1. You could just pull out one square and say, yeah, I made a square. So 1 would be a perfect square. How many squares do I have here? 4 is the next perfect square because this is 2 squares by 2 squares. It's like finding area. 2 times 2 is 4. Then I would increase 1 each dimension, so I would have now 3 times 3, or there's 9 squares. Then I increase to 4 by 4. That would be 16 squares. You count them if you don't believe me. Get the pattern. 5 by 5 is 25. 6 times 6 is 36. So these are actually what I have on the back of my wall. And it's the top row, because that's what we're talking about, is just the squares. The bottom row is going to be the perfect cubes, and we'll get to that later in the unit. Okay, so let's list out the perfect squares in order. We'll put 1, but I'll tell you 1 will never be used very often in this lesson because it doesn't do us any good to simplify with it. But then we said 2 times 2 makes 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5, 25. 6 times 6 is 36. 7 times 7, or 7 squared, is 49. 8 squared, 64. 9 squared is 81. 10 squared is 100. We'll go a couple more. 11 squared, or 11 times 11 is 121. 12 times 12 is 144. 13 times 13 is 169, and then actually 14 times 14 is 196. So kind of funny how the digits just switched there. And the last one I would really try to memorize is 15 times 15, and that's 225. We usually don't go bigger than that, but I'm not saying it will never happen. It might. Okay, so if we learn about perfect squares, now let's talk about a non-perfect square. A non-perfect square is a number that cannot be arranged into a square. It would be only a rectangle. In other words, a number that has no duplicate factors. So when we start out learning this, kids will say, okay, well 6. 6 is a nice even number. It must be a perfect square. But if you had 6 little squares cut out on your table and I said arrange them into a square, you couldn't do it. You could put them in a 2 by 3. That makes 6, but that's a rectangle. 1 by 6. That makes 6, that's a rectangle. A 3 by 2. See how there's no multiplication of a number times itself, so it's not a perfect square. Same thing with 12. You would think, but it's not. We would make a 3 by 4, a 1 by 12, a 2 by 6, a 6 by 2, a 4 by 3. There's no duplicate factors. There's no multiplication of a number times itself. So our job is to take these non-perfect squares and try to simplify them or break them down so that they look a little nicer. So what I want you to think of is we just proved that 12 would not make a perfect square. But I could use a smaller square size or shape and then have multiple of those. So I want you to think about having a square with 4 little squares in it. So that would be 4. And then I'd have another 4 and another 4. So I broke them down into squares, but now I have multiple of them. I have 3 of them. So what you're going to do is rewrite the square root of 12 is the same as the square root of 4 times the square root of, I don't know why I put another square root there. I'll tell you why, because usually I don't write them both under here. But I wanted to the first time. Okay, so see how 4 times 3 is still 12? I just split this number up. One of the factors, one of the pieces of the multiplication is a perfect square from our list. It's 4. And so what I really do is have square root of 4 times square root of 3 like this. Square root of 4, since that's a perfect square, needs to get simplified. Well, 2 would be that number because 2 times 2 makes 4. So square root of 4 is just 2. Not square roots of 2, just flat out 2. But what do I have left over? Square root of 3. So now it's actually 2 times the square root of 3. Okay, then 18. Nice even number again, but it's not a perfect square, it's a rectangle. So you would look at your list of perfect squares. What could 18 be divided by? 9. You could have a box of 9 and a box of 9. So I'd rewrite this as the square root of 9 times the square root of 2, which is the same thing as both of them being under the radical like what I had above, but I get to where I do this. Square root of 9 can be simplified. What number times itself makes 9? That's 3. So it'd be 3 square roots of 2. And you might think, well, these look very similar. Are they the same thing? They're not. Let me get a calculator and show you. Okay, here is the square root of 12. Put in my calculator, the decimal is 3.46 something, right? It's called an irrational number. It doesn't repeat and it doesn't stop. And then I tried my simplified answer, which is 2 square roots of 3, and I put it in like that. Same thing. So I did not change the value of these two expressions. I just changed how it looked. And then let's do the square root of 18. Totally different number. And if I put in 3 square roots of 2, look, they match. So again, I did not change the value, I just changed how it looked. That's what simplifying is all about. So we've got 4 more here. I'll do the first 2 with you, and then I'll let you pause and try 3 and 4. Our job is to figure out what I could break 28 into. One of the numbers has to come from this list because they are the only perfect squares I know of, right? Unless I kept going with my list. So 28, I start at the top part, cannot be bigger than 28, so that's out. 25, obviously no. 16, no. 9, no. 4, yes. So I'm going to rewrite this as, it's a square root of 4 times the square root of 7, right? 4 times 7 makes 28. Square root of 4 is just regular 2. So this would be 2 square roots of 7. And that's my answer. Next one, square root of 50. That's a pretty easy one. Think of money. 25 would be my number. So I'll split this up into square root of 25 times the square root of 2, because 25 times 2 makes 50. Square root of 25 is actually just 5. So it's 5 square roots of 2. Okay, I want you to pause and try 3 and 4. Okay, I guarantee some of you got these wrong, and I bet I already know why. You didn't pick the perfect square 36. You picked something smaller than 36 if you got it wrong. Am I right? Because this is what kids want to do. They want to look up here and say, okay, well, 108, it does divide by 4, and they stop. You have to pick the biggest perfect square, the biggest you can. That's kind of like if I had a fraction of 16 over 32 and I am asked to simplify this. Well, they're both even. I'll divide them by 2. That would get me 8/16, and I stop. Is that fully simplified? No, I should have divided out a 16 from the get-go. That's the same thing you're doing. You have to pick the biggest perfect square you can. So what that means is the radical that's not the perfect square should not have a perfect square still in it. So usually there's some kind of prime number, not always, but usually. So like, for example, if you would have used 4, let's see, 108, square root of that would be square root of 4 times square root of 27. It's all fine and dandy, but 27 can be divided by another perfect square of 9. So you would actually have to go again. So try to just start at the top of your list and then work down this way and instead of starting at the bottom and working up. And you'll get better with it as you keep practicing.